So, good morning, everyone. Such a large room for so few people, but I think people will keep coming into the room, so I hope more, or we should go out and round them up and bring them into the hall. Thank you for coming to this special International Prize lecture from our colleague here, Mickey Strasser. I just wanted to briefly say to you exactly what is the Asahiko Taira International Scientific Ocean Drilling Prize. It's in recognition of outstanding disciplinary research accomplished in ocean drilling, and is only one of 2 prizes given by AGU. And it's a partnership between the American Geophysical Union and the Japanese Geoscience Union. And it honors a good colleague of many of us who are sitting in this room, Dr. Asahiko Taira of the Japanese Agency for Marine, Earth Science and Technology, better known as JAMSTEC. And Dr. Tai has an extensive background of more than 40 years in geological research, and his area of focus include tectonics, paleoceanography, and ocean drilling science. And I'm sure that my colleague Mickey is going to tell you more about the research that was conducted off the Japanese shore. How do I change this? Click the mouse, maybe. Okay. Now, the actual prize, the criteria for the prize, it's for outstanding and transdisciplinary scientific contributions enabled by ocean drilling. It is given annually, and this is only the 3rd time that it has been given. The nominee eligibility is you do not have to be an active member of AGU, but it probably is very nice if you are, and most likely you will be if you're involved in ocean drilling. And you must be an active early career to mid-career scientist within 15 years of receiving your PhD in any discipline, and you must be making an impact in the field of ocean drilling. Our recipient, the 3rd recipient, 2017 recipient, is Dr. Michael Strasser, professor in sedimentary geology at the University of Innsbruck in Austria. Now, Mickey did his, many of his colleagues, I'm sure, call Michael Mickey, so please forgive me. I know Michael Strasser is Mickey Strasser. He completed his diploma at the ETH in Zurich, and for his diploma, he had the best diploma thesis of that year in 2003. And I have to say, he was one of the best students that I ever lectured or examined in earth science. He continued with his PhD at the ETH in Zurich, and he received it in 2008, and for that he received the ETH Silver Medal for an outstanding thesis. The title of his thesis was Quantifying Lake Quaternary Natural Hazards in Swiss Lakes, Subaquatic Landslides, Slope Stability Assessments, Paleoseismic Reconstructions, and Lake Outbursts. Now, I think you can already see there's a similarity to what he was doing in his postgraduate career. After completing his thesis successfully, he spent 3 years in Marem at the University of Bremen as a fellow sponsored by the Swiss National Science Foundation and the Marem Association. From 2011 to 2015, he returned to Switzerland to become the SNF assistant professor in sediment dynamics. And following that, he was given a full professorship in 2015 in sedimentary geology at the University of Innsbruck in Austria. Now, you might wonder why someone goes into ocean drilling from lake research. And our concept of lake research in Switzerland is that you do everything. You learn how to drive the boat. You work in all kinds of weather, doing direct drilling. You conduct the seismic surveys yourself. You crack the wrench, and you supply the ship with, so you're doing everything that you have a huge crew to conduct on an ocean drilling vessel. But Mickey became interested in ocean drilling before he finished his master's thesis. In September 2002, he joined the JOIDES resolution. Where was it, Mickey? It was in
Acapulco.
Acapulco, yes. And here he is waiting to begin his first ocean drilling cruise and his life at sea. And subsequently, Mickey has participated in 3 different IODP expeditions working in the Nankai Trough as a sedimentologist, as a PI of the proposal and stratigraphic correlator, and also, finally, his last expedition was as co-chief scientist. And here you can see Mickey is still doing a lot of the things, a lot of the work that he might have done, core logging, checking out the core, discussing with people, working on his computer, but it's not quite like doing lake research in Switzerland. But we don't have oceans in Switzerland. And finally, the citation, the official citation for Mickey's prize is for outstanding contributions to the investigation of submarine mass movements by multidisciplinary approaches through scientific ocean drilling. And finally, I introduced the slide, but first, the official nominator of Mickey Strasser would like to say a few words.
Well, thank you, Judith. I'm Yasu Yamada from Jamstack. It's a great honor for me to be as well. And what I did was just summarize what he did, what Mickey did, and submit it to the selection committee of the prize. So I'm really happy that the committee members well accepted the prize. What he had done in the past. So it's simple, and I'm really appreciating Mickey. And also and saying many congratulations to Mickey Strasser. Yes, and you too.
Well, thank you very much. I'm going just to quickly change this. I hope I can do this. How do I get out here? Here. Okay, I'm getting there.
Okay.
Okay, here we go. Good morning, ladies and gentlemen. Thank you very much to Judy and Yamada-san for introducing me. It's really a great pleasure to be here, and I feel deeply honored to receiving this prize. And before I start, I would actually quickly like to introduce you my co-author team. On this talk, because obviously such a prize and such research you never do alone. And it is actually, I have more co-author than people in the room here. That's kind of cool. And it is this fantastic crowd of people, very different personalities, bright, smart people, various disciplines, which I had the pleasure to be exposed to throughout my career in sailing in these 4 expeditions. And as many of you know, is like when you are at sea over these several weeks or months of time, you share ideas, you develop concepts together, and that's really what makes the research so exciting, and maybe also the scientific advancements are so major because you share these interdisciplinary thoughts with great people. I also would like to thank my wife Bettina and my whole family that actually supported me and allowed me to sail on all these cruisings, being away from home. I also just would like, because just being on the ship is never really, the research just starts back home in the lab. And in the second part of my talk, I'm going to introduce some exciting results that have been produced by PhDs and postdocs at ETH Zurich, Katrina Kremer and Rui Bauer. I'm going to lay the latest results. And now my team in Innsbruck, Jasper Mornot, Arata Kyoka, and Tobias Schwestermann, which are working with me on the current results and hopefully some exciting future research. Okay, so coming back to my talk, slipping and sliding. When I learned that I have the chance to come to New Orleans, like the city of music, and do a talk, I immediately kind of thought about, like, okay, it has to be something with music. So this is a song title by Little Richard, which was later performed by John Lennon and kind of got famous. So I will kind of go through this slipping and sliding over the next 50 minutes or so. But actually, it really nicely wraps up everything I'm going to talk to you today. It's all about slipping, earthquake slip, and sliding, sea floor, subsurface sliding instabilities, and we are going to talk about how these are related to each other. What can we learn from one to understand the other one, or what can we learn from this one to maybe get some inferences on the other one? So it's really all about slipping and sliding to understand and capture the Earth in motion below the seafloor. So what I'm going to do is I just give a brief overview on how this theme developed. And actually, I'm really pleased that this is the Taira Prize, because it was Dr. Asahiko Taira back about that time when I was born, that when he and like Dan Carrick and others went out following the paradigm shift of plate tectonics, which was developed on the mid-ocean ridges. So that's where they realized, okay, there is extension there. So if there is extension somewhere on the plate tectonic theory, there has to be compression somewhere too, right? So Taira and others on the first DSDP legs in compressional settings, they went out, they did some first seismic reflection profiles to image the compressional part of the plate tectonic systems, and they found this deep sea sediments, turbidites, trench turbidites in the trench, and Asahiko Taira really was among the first to kind of show that seafloor sediments and deep sea turbidites are scrapped off, forming this accretionary prism, which eventually helped to decline the geosyncline theory and kind of prove that yes, there is not just extension in the mid-ocean ridges, but there is compression there. And then over the several decades to follow, DSDP, ODP, along with the as important site survey data where reflection seismic is being collected to image the tectonosedimentary section of these compressional systems, and drilling and coring revealed several samples from the deep sea trenches and from deformed rock. So the concept of understanding subduction zone plate processes has evolved. By about the time when I started my studies at ETH Zurich, there was pretty robust conceptual understanding of subduction margin processes. Also from seismology, there's a magnitude 8 subduction zone earthquake once per year on average somewhere on this planet, and the concept of having different asperities. Do you see my? Yes, you see it. So having different asperities that may lock and accumulate strain based on plate boundary, and maybe something like, maybe on a regular scale, depending on plate motion and stress conditions or so, there's accumulated strain that get released by subduction zone earthquake, which are forming in this seismogenic zone. And somewhere up dip, there got to be some kind of aseismic zone here and another aseismic stable zone gliding here. So that was about the concept. And then, again, it was Asahiko Taira among the leading fathers of this gigantic, great research infrastructure that Japan built, with the eventual aim of drilling into this locked zone of subduction plate boundaries. And that was the IODP science plan some 15 years ago or so. And we are really getting close to get there, hopefully next year, to actually reach that 20-year target. So that's very exciting. So my first exposure to this research, as Judy mentioned, was Costa Rica, when I got the chance to participate in that fascinating program, what was called back at that time the undergraduate student trainee program. So during ODP time, when there was engineering legs, where there free berth or so, then they would sail a student trainee, and I was the lucky one. And before I go into some of the results from the Costa Rica, I really should acknowledge my professors and mentors at ETH. I cannot overemphasize more by the fascinating lectures I got from these people, and also just like the motivation, support to apply for this program. You know, I grew up in the mountains. I've never seen the ocean before, so this is really kind of this excitement of independent where you are on the earth, that this program really is about understanding the big challenges of our planet. So I was lucky enough to get elected to sail on that expedition, and it was not quite the first, but it was among the first expedition where the scientific idea changed from like a rather static understanding of plate conversion system to going into the monitoring. So scientists realized, okay, we gotta do monitoring. These are dynamic processes. So the major objective at that time was to deploy such a cork systems here, which you may not see the detail. It doesn't really matter what the details are. The fundamental idea is that you use borehole observatories and deploy instruments down there to measure and monitor processes at depth. And that's what has been done. So there were, and these are some results published by the group by Miriam Kastner and Evan Solomon and Davis and Fillinger here. And basically the upper part you see geochemistry. So there was what they call an osmosampler in that observatory. This is basically a coil that sucks in by osmotic pressure the pore water, and by knowing the pump rate, you kind of get a time series of geochemistry. So we see, what do we see? Some elements, where are they? Okay, sarin and pore pressure, and we calculated flow rate as a time series here. And below, these are GPS measurements from on land Costa Rica, where they see some events in how the coastline moves. And there were some couple of month lasting events here where the coastline had some GPS movements, which have been interpreted as either slow slip earthquakes or very low frequency earthquakes on some movement on the plate boundary that is releasing some strain over a couple of months' time, and this obviously associated to some pulses in pressure, to some changes in geochemistry. So these are what like in my talk now I consider as this monitoring, capturing slip processes or processes in the fault zones themselves that somehow relate to plate deformation. And by now, there's a series of different types of earthquakes, a different type of slip processes, ranging from very slow rate to the big ruptures. And scientists all over the world, by using this program, are capturing these processes. So yeah, okay, that was just the wrong direction. Here we go. But as Judy introduced, I'm a sedimentologist. So what actually really fascinated me most during that cruise was these strange cobbles of shallow water limestones in the lower trench slope set. So very much as Asahiko Taira some 30 years before me, I realized, oh, there is some fascinating processes going on these deep sea trenches, where we have sediment mass transfer to the deep sea. And I also have to acknowledge the people, like Peter Clift was my mentor, and like Adam Klaus and the co-chiefs, they really encouraged me to kind of develop to become a sedimentologist and that was really a great experience. So that was then the time when I realized that there is another world out there that not just looks at earthquakes and slip, but actually also at sliding processes. So here we go, slipping to sliding. When that was about the time when also like multi-beam bathymetry came up, and we started to image these tremendous large-scale instabilities, like here the Nicoya slump offshore Costa Rica, and the sample here where I, as a sedimentologist, realized, oh, there is some mass movement down here. It's just a little bit more to the north. And these are like work by Roland van Hune or so. So there was like big scale landslides, and this is textbook. This I knew. This I learned in my class already 100 years ago, or not quite, but 90 years ago. There has been actually like an observation that slip leads to slides earthquake slip. There was an earthquake that causes a submarine landslide. And why do we know this? Because the earthquake here in Newfoundland had these cable breaks, and what you see here in numbers are minutes after the earthquake when the cable broke. So this is really the textbook example. By now, Dave Piper and others are doing the tsunami modeling, and they can show that the observation where 4 people died from that tsunami really fits our understanding. So that was like, that nicely fitted together. And by now, using multi-beam coring, mainly shallow coring, reflection seismic, there is quite a good understanding where such big landslides occur. And I'm just choosing 2 of my favorite examples here, the Riloca slide in Chile. And just look at the scale here. So this is a 2-kilometer headscarp, and this is an 18-kilometer arch. So these are huge blocks that display mass into the trench here. And that's another one, tremendous, the Roratorio landslide in New Zealand, which actually kind of the entire margin seems to be destabilized. So while the IODP community was making big advances in understanding slip processes and subduction zone processes, another community kind of grew big. And I've seen Roger Urgelis and other people here. So this is really, so there have been 3 UNESCO programs on understanding submarine landslides and their consequences. There have been a series of books and conferences, one of which was lead edited by Yamada-san. I don't know which one it is here. So there is a tremendous amount of information, like having studied this subaquatic or submarine processes. And still today, or like through that processes, these are some of the main findings. So submarine landslides are key agents for sediment mass transfer to the deep sea. They can produce tsunamis, which may impact coastal communities and infrastructure, and they can damage very expensive and critically important installation, as we've seen in 1929 when the telegraph cable offshore Newfoundland. So you could say maybe, well, I don't care about telegraph cable. I use internet. But remember, 95% of our internet communication go through seafloor cables. It's still the most efficient way of transferring big data. And so this is actually, I'm worried. If I cannot check my emails for more than maybe 2 hours or so, I get nervous. So we really need to understand these processes in order to mitigate that hazard or risk. Okay, so what do we do then to study this? So what are the research questions and the challenges? And there are many. I try to summarize like my 3 most important ones. So why certain slope fails whereas other remain stable? And I don't think we have a uniform answer to this yet. Why some slides remain small while others grow large? And when and how often do they occur? So these are sliding questions. I could easily just replace slides by earthquakes, and we would be at the same picture, more or less. How do we know exactly which asperity is going to fail when? How do we know how earthquake rupture become big or slow, and when and how often do they occur? So like at least, I mean, those are different processes, but at least the fundamental question behind that are somewhat similar. So I think the communities can learn a lot from each other. Okay, so what we really need to address this, in particular for submarine landslides, we need to access samples and in situ conditions to constrain the parameters, control size, runout, and dynamics. We need to access samples from submarine slide deposits to constrain the magnitude and frequency, and this will lead to hopefully advance our understanding of how does this relate to varying preconditioning factors. By preconditioning factors, I mean things like tectonic, uplift, long-term sea level changes, sediment supply system that somehow control the stability condition of ocean margins. versus trigger mechanisms, which may be an earthquake or a fluid flow pulse or some kind of other transient instabilities that may then destabilize large slopes. So these questions the submarine landslide community kind of evolved, and it was an exciting time when we went from the IODP science plan, like the integrated ocean drilling science plan, to the International Ocean Discovery Science Plan around 2009, when actually, again, people from the submarine landslide community, including myself, had good momentum to bring in these research questions into the IODP science plan. And in the IODP, like the integrated drilling program, there were at least 3 major expeditions dedicated to this research theme. One was led by Peter Flemings and Jan Beermann in the Gulf of Mexico, where they studied hydrogeology processes, fluid flow processes, and how this may trigger instabilities in what I here refer as like a passive margin setting. Although there are some exciting papers coming out there that even there you may need an earthquake every now and then to actually destabilize some of these instabilities. There has been an expedition led by French and Japanese co-chiefs on volcanic island collapses, these huge tremendous flank collapses here in the Lesser Antilles. There has been an earlier drilling by JR once in Hawaii to investigate these big volcanic island collapses, which is also like a mass movement sliding type of research question. And then there was the Nankai Trough Nantra-Slide Subduction Zone, which is like my scientific baby, which I was leading together with some others. So I will come back to that in a second, but I just would quickly say, for those that don't know, that actually JR is on a mission for studying submarine landslides right now, steaming towards the Hikurangi margin offshore New Zealand to study this beautiful Tuhaini slope here, which has some links to gas hydrate. So there is an interesting research question on how gas hydrate may stabilize or increase instabilities on creeping landslides. So landslides, similar as earthquake, may not only just be sliding into like one instantaneous moment, but also may be creeping and have slow sliding, not slow slip earthquake, but slow sliding landslides. And this is like one research question which is being addressed right now by JR. Okay, but I would like to come back now to like my first major scientific presentation. Like within this lecture, I'm going to give you 2 examples. One is now the Nankai Trough, where I introduce you to this submarine landslide history project. And in the second part, I will talk about the Japan Trench, where we think we learn a lot about how earthquake and sediment mass movements link to each other. Okay, so the Nantra-Slide project, the Nankai Trough Submarine Landslide History, was suggested as a APL, an ancillary project letter, because I knew the ship is around there anyway, and I learned that the ship needs contingency options. So I thought maybe strategically clever to present some contingency options, and that's what I will show you in a second. So the research questions are really those that I introduced you before. It is all about trying to understand what's the magnitude and frequency of mass wasting in a accretionary prism setting is, and how it relates to tectonic and earthquake activity in particular, because that was kind of our paradigm, or at least my paradigm at the time. I thought, okay, maybe we get a record of earthquake. That's what I learned in the lakes, that it may work, so let's try it in the ocean. But maybe versus other driving mechanisms which we need to study. Okay, so, and for those that are kind of familiar with the Nankai Trough, so this is really integrated into the big program there, which is the IODP non-anthracite seismogenic zone experiment, which I introduced at the beginning, where GQ uses drilling riser technology to drill through the inner accretionary prism here all the way into the locked zone. Down here, it's not quite there yet. The current depth is around 3 kilometers, and there are really solid and hopefully will turn out to be successful plans to go into the seismogenic zone next year. So this has been a multi-stage effort to sample and instrument the plate boundary faults across the up-dip end of locking and seismogenic megathrust rupture, and it started 2007, and hopefully it will culminate in 2019. So what is it? What is the achievement so far? Just a brief summary. We have drilled 15 drill sites. The maximum depth currently is 3,000 meters, and which is the deepest hole in scientific drilling. And overall, over these 10 years, about 150 scientists from almost 20 countries sailed. So that's what was my introduction. So it's really international. And so the frontal plate boundary thrust and the shallow spay fault has been sampled. There are first cores and cuttings from the deep interior of the Nankai forearc. 2 permanent observatories have been installed, and more than 200 papers, and probably more. I think this number, I looked it up last in summer, so they're still growing. Many more are in the work. And I kind of, the target is not reached yet, but already a lot of scientific accomplishment have been achieved. And there are just very few ones. I mean, I could probably give a 2 or 3 hour lecture on all this and kind of summarizes all this. I just be very selective and show you some of the most exciting ones, which kind of goes into what I introduced you for Costa Rica already. And this is result from monitoring. So this is now here a time series looking at these monitoring sites here at site CO10 in the shallow hanging wall of this megasplay fault zone here. And based on these data, this is pressured, it's a pressure sensor. Based on this data and also using a lot of OBS stations around that were listening to slip processes at the plate interface, they could show some interesting relations between slow slip earthquakes or very low frequency tremors and deformation recorded in these observatories, and could publish this science paper and actually also show that there is maybe a link between triggering one of the other. And this is not really my specialty, so you see I'm not co-author here, but this is very fascinating and kind of leading edge observation of slipping processes along the plate boundary. Another, at least to me, one of the major highlights is in understanding slipping processes by anthracite, is this paper by this fellow here, Arito Sakaguchi, who took some samples from the shallow fault zone here, so at the very frontal thrust here, the coring drilled through the frontal plate boundary thrust here, and based on lots of deformation and scaly clay fabrics or so, they could identify the zone which may have the major shear on it. So slip processes were inferred from textural implication. But what he did, he used vitrinite reflection data, which is kind of an organic proxy on how much the rock was heated. And then he does some modeling, and I guess the details of it may be partly debated, but overall the concept was that maybe there is a proxy for having frictional heating induced by slip all the way to the frontal thrust. And remember what I introduced at the beginning, that's not possible based on our conceptual model, right? Because we said at that time, the concept was mainly seismically locked, and then the very shallow part would be aseismic. So that's one of these, and actually, and this always produces goosebumps when I give that talk. Please look at the publication date of that publication published in Geology. It was 8 March 2011. It was 3 days before the Tohoku earthquake hit, and I'm going to talk about the Tohoku earthquake in 10 minutes or so, and I will show you that slip to the trench is occurring. So 3 days before that event, there was a paper in Geology that suggested maybe we may have slipped to the trench. I think this is really exciting, and maybe the community has not really realized that this fellow really was transformative. Okay, so now a study where I had been involved myself. And this kind of goes to the same concept. Let's just go back. So we still are at this very, very frontal thrust here. And we still are in that fault zone that may have slipped in the past. So there, Natasha Riedinger, and you will see in the next in the next few slides, I like to work with organic geochemists. It's really exciting, and that's what is IODP for, right? You learn to get to know people. So I will acknowledge here the organic geochemist Natasha Riedinger, because she looked at deuterium isotopes from methane samples across that. So here's the detail, the borehole all the way down to the deformed zone, just overlying the décollement here. So she looked at the deuterium isotopes and sees some anomalies, which, and please don't ask me the details, but which the organic geochemist would interpret as in situ methane production by some kind of bacterial processes. So yes, in the shallow subsurface we have microbial processes going on, that's okay. And then there is a signal which can be interpreted as diffusion. But then, somewhere down here in 500 meter subsurface, where we come close to the deformation front, there is another, like based on this proxy, based on this methane carbon isotope proxy, another indication to have active microbial processes in the deep surface. And this is where actually the other paper by Sakaguchi has proposed maybe frictional heating. What Natasha then also did, she looked at the anomaly of alkalinity in the pore water profiles, which if you have diffusion, it would just be a straight line because it diffuses and the alkalinity would be more or less a straight line, unless you have microbial processes that control the alkalinity profile. So yes, there is some anomaly up here, and there is an alkalinity anomaly down here, which basically means that whatever triggered that microbial process is either still going on or not too long in the past. And she did some diffusion modeling and kind of suggests that maybe something like 300 to 400 years ago, there might have been some kind of impulse that maybe have added some heat or some fluid that reactivates recalcitrant organic carbon, and this gives some time constraints on maybe tectonically transient temperature increase, which might be that we have at least an idea of dating when the slip to the trench occurred. It's really just formulating hypotheses based on exciting data, and this is exciting research that can be followed in the future. Okay, so again, I'm a sedimentologist, and guess what? I was mainly fascinated by the strange rounded mudstone pebbles and the deformed sediments. So what my contribution to the NANTRO size project was that I worked up the stratigraphy of this splay fault zone and looked at when mass movements occurred, and I was very excited as a young postdoc that I have a 2 million year of mass movement activity, which maybe the frequency somehow relates to fault activity, and I kind of started to think about, okay, how would the fault activity be, because I really wanted to understand my mass movements. And then I have to do another big acknowledgement to now my postdoc mentors and advisors, these fellows, Achim Kopf, with whom I was postdoc in Bremen, and Greg Moore, the co-chief science of 316, Kitty Milliken, Mike Underwood as the sedimentologists, and they kind of actually hinted at me that yes, mass movement is nice, but actually what you're doing here in reconstructing the splay fold movement is actually really innovative, and nobody has done that before. And I said, okay, if you say so, let's publish in Nature Geoscience. And so thanks to the help of senior scientists who guided me on like where the exciting science may be, we used basically this mass movement frequency and related splay-fold activity and could show that the splay-fold activity varies through time, which is also an interesting concept if we think on like what are the pulses and frequencies of tectonic faults over long term and how they may relay on the short-term cycles of faults and eventually earthquakes in these settings. But then I kept going from this rupture or slipping history on the sliding history, and particularly Greg Moore was very influential in helping me to think big and develop this landslide aspect and how this links to subduction zone processes. And that was the time when we formulated that APL to investigate the submarine landslides in that margin. And basically what we did, we identified in the 3D seismic cube a little bit down slope, the splay fold that crops out here, a nice and continuously stratified slope basin that has a beautiful succession of several mass transport deposits, some of which were really large and which could be reached by drilling, and we also get the chance to do some logging in Expedition 338, so logging and coring to investigate the Pleistocene to Holocene succession of mass transport deposits and how it relates to splay fold activity. And here, the team, just to acknowledge the co-chief scientist of these various cruises where we had some contingency time to do the drilling, and with whom we developed all the science. This is about the time to also acknowledge the real good people working hard on the ship to get us. I start on the right-hand side. It's actually MQJ that actually do the drilling and CDEX and the expedition manager, Nobu, Sean, and Lena. And I could have said the same for JR on expedition on ODP 305, Adam Klaus. So really, these people they deserve the same acknowledgement as scientific collaborator when we do some scientific advancements in ocean drilling. Okay, so let's look what are the scientific advancements from our NanTroSlide project. And these are the four main subjects. So we got 50% of sediments are actually remobilized. We have the occurrence are about 3 orders of magnitudes longer than the earthquake cycle, which kind of says that the emplacement of mass transport deposits do not really relate to earthquake, but may have another conditioning factors. And there are some other more detailed findings here. This is just a summary of the entire drilling. I just would like to highlight a few things which also led to development of new techniques, how we study this. And one of which certainly is to use CT scanners. I've been in a session yesterday where basically a lot people are doing CT scanning now, but with GQ we already did that in 2007 and published the first paper in 2012 and realized that actually we can see much more rather than having the visual image here, which sedimentologists just would describe as greenish gray silty clay. If we look in CT, we actually see deformed strata. So we looked at it a bit in more detail and found that these are actually pyritized worm tubes that from bioturbation they get pyritized and they can basically used as a proxies. And you probably have been steering at this. So these are elongated high CT numbers, and they kind of give a shear. So they are all aligned. So we have a proxy for shearing in this, and this has also been using another proxy by Kanamatsu, who looked at the anisotropy of magnetic susceptibility, using basically how the ellipsoid of the anisotropy direction is related to the different zones, and based on this he can also kind of infer either shearing processes or slumping processes, slumping and folding. So these are some, and I'm not going in detail, but just like some of the highlights where ODP is not just kind of bringing up results that advance our understanding, but actually is developing new techniques as well. So I would like to also talk a bit about this one here, where we learn that actually the order of magnitude in terms of recurrence interval is much longer than the earthquake cycle. I think that was a non-expected result. And there's a paper which came out this summer by Katrina Kramer, and what she did, or what we did, is basically we just said, okay, we need to have very, very precise dating. We need to know exactly when the emplacement of these processes is. So what she did in collaboration with tephra stratigraphers is to went through all the tephra layers, so these are data tephra layers, and we did isotope stratigraphy. So we just did an isotope stratigraphy curve on this, and in order to see when they occurred. We also, for the youngest one, we did some radiocarbon dating. So in here you have the depth below seafloor from the first MTD here, it's 140, and we have the time here, and we see that the emplacement of this one, and here's the sea level curve, no, it's the benthic stack curve, delta 18, and we see that the emplacement of this was somewhat during the transition from the kind of interglacial to from the glacial time to the interglacial time into the Holocene. And we do this for all MTDs. This is just a comparison, the isotope data from the drill hole here, and using tephra stratigraphy to match it to the isotope stack curve from benthic foraminiferous in the Pacific, or the global stack, sorry. And then down here we see the emplacement of the MTDs correlated to a climate curve. And we see there is an interesting coincidence, or an interesting timing that actually, that's the first highlight here. It's the first long-term record. And then it also coincides that the slide events have had during interglacial periods. So we propose some climate forcing as a preconditioning factor. We hand wave about some hydrate hypothesis and so on, but this is a lecture, so I should not hypothesize here. I just wanted to present you this fascinating data that again allows us to think different and in our way of sliding. Okay. In my remaining 7 minutes I have, I think I need to speed up a bit. I would like to now go to the Japan Trench, which obviously the 2011 earthquake allowed us to really think different about earthquake processes and how slipping may induce sliding. And so the Tohoku earthquake was the first event of its kind worldwide where the entire activity was recorded by offshore geophysical and geodetic instruments. And there have been a series of fast response cruises that caught slipping and sliding processes in action. This is just a compilation here of the Japan Trench, and in red we see all the cores that have been selected after the earthquake. So basically we have a really nice coverage here. And just flip through a few of the highlights here. Most of you may have seen this. One thing that Toshi Fujiwara did was differential bathymetry, so he actually could show that indeed the slip all the way, or the deformation was all the way to the trench here. And Suichiro Taira published this differential reflection seismic line, which I like to show in my talks. This is before the Japan Trench before the earthquake, and this is the Japan Trench after the earthquake. So we just nicely see, I go again, before and afterwards, how the deformation reached all the way to the trench. And here's another great person which I have to acknowledge, because he helped me to get a German rapid response cruise going when we went to the Japan Trench and looked at this along strike mapping and ground truthing by core. So we were together with the Japanese colleagues among the first one to actually get samples from the Japan Trench, and we proposed that there, like, some of the displacement that comes all the way to the trench actually may trigger some sliding events, some rotational slumps that are adding to this deformation. I guess many of you are familiar with the Japan Trench JFAS project that drilled into the slip zone and did this temperature measurements. So what I showed you before, the Arito Sakaguchi paper that used proxies to induce, to measure seismic slip and heat. This experiment actually measured the heat. That was really exciting. And I'm not going in detail, but basically by the heat decay and the time after the earthquake, Patrick Fulton and others here could basically calculate stress drop and frictional coefficients here. So this is then really now the time to say that we are in a paradigm shift again. I wouldn't say it is as substantial as going from the geosyncline to the plate tectonics, certainly not. But it is a paradigm shift in our understanding of the shallow up-dip limit of seismogenic zones. So these earthquakes, they do slip all the way to the trench. And, right. So this is then kind of brings us to where the future might be. So this is really a topic that needs to be investigated. And there is the JTRAC proposal led by Kodaira-san, who is trying to understand what are the governing mechanical, frictional, and situ stress constraints on the mega thrust. And also the question kind of, is there a superimposed earthquake cycle? And what we really need there is what would control the recurrence pattern. So we need somehow, and you remember my questions for the submarine slides, it really was the same, like how often, what are the recurrence patterns, how often do they occur? So this is where we come in now, when we study what are the fingerprints of the earthquake. And now we go to the deep trench, and there we really learn some fascinating things about the Tohoku earthquake. Here is data by Oguri, where they had video observation of a sediment cloud that still 4 months after the earthquake was still 40 meters thick. So this was a big amount of fine-grained sediment that somehow was steered up and made all the way to the trench. And it has been cored, and using radionuclide, lead-210 and cesium, these very fine-grained sediments, which is just basically mud, homogeneous mud, unstructured homogeneous mud, contains all these high, very young sediments. So this suspension cloud must basically be just very young sediment somehow steered up and transported to the trench. Yeah, thank you. So in that 2011 cruise, we took a core here and we studied the deposits, and we went back in 2016 to take yet another core. And actually what we did, we resampled the same location because we wanted to study here some chemical proxies which are hypothesized to may be indicative for sediment remobilization like manganese, and we looked at the pore water geochemistry to kind of try to track how a signal goes into the stratigraphic record. And maybe what we found here is actually that even an aftershock may have triggered some additional sediment remobilization. So actually the characteristic fingerprint of an earthquake, of a major earthquake, may actually be a succession of several deposits overlooking origin. So one thing which we have to be aware of in these very young sediments, that this is remobilized, that our thinking of sliding may be wrong. Because a landslide, an earthquake-triggered landslide, will not remobilize young sediment. This will be a mixture of very old sediment. So here Jasper Mornard, based on studies in lakes actually, proposed that maybe it's just superficial sediment remobilization. And Cecilia McHugh in her geology paper actually estimated, based on the radionuclide, that indeed it would just be a huge amount which may relink to the rupture zone, just peel off the top 5 centimeters or top centimeters. And this may be a new process of how shaking and may affect sediment remobilization. And it turns out that actually these superficial sediment failures may create these mud density flows that then go into the terminal basins that form this nice stratigraphy of mud turbidites, which Kenny Gehara worked up in his EPSL paper, and show these event stratigraphy. So there might be a nice tool for paleoseismology. And I'm running out of time, but I just have to show you the highlight of my talk. We got interested in studying these event deposits in more detail. So these are the Tohoku layer and some older layers that relate to historic earthquakes. And this fellow here, Rui Bao at ETH, just got his Nature Communication paper accepted. And you are looking at a radiocarbon C14 dating profile here. This is radiocarbon age. 7 meter core, 100 radiocarbon ages here. And what we see is that actually the event layers are a bit older than the background sediments in terms of bulk organic geochemistry. A radiocarbon age. So what this means that there is episodic earthquake-triggered gravity flow driving supply to the deep sea trench. Bao also calculated the flux of organic carbon in these event deposits and proposes that actually the earthquake have like 2 order of magnitude increased carbon flux into the deep sea trench. And the deep sea trench here is 7 kilometers deep, so that's the Huddle Ocean. So this is a very interesting new thinking of maybe how carbon comes down in the deep sea trenches and supplies the community. But many of you may say, okay, carbon, how that radiocarbon dating below the CCD would not work. What actually this paper also proposes using the thermal fraction, like heating up the samples and looking at the different thermal fractions. So yeah, Judy, I'm sorry, I could keep talking, but let's just read the paper. It's coming out in January. It's really exciting. I mean, this is more like a dating thing here, because dating is a challenge in the deep sea. But the most fascinating thing are these. So I'm not going to introduce what we think we could do in order to study all this, because there is an IODP proposal to go deeper and get a lot of mission-specific shallow subsurface piston cores across the entire margin to go back in time, to study earthquakes longer, to study carbon flux to the deep sea. A lot of fascinating research. I hope we get a chance to do this, and hopefully in maybe 5 or 10 years, I stay not here as a prize recipient, but as an HU participant, and can introduce you all this exciting data. And I would like to end my talk in time. I'm sorry for rushing through here. Just like to summarize a very simple statement here. Earth in motion along subduction pattern are dynamic processes, such as those leading to and resulting from earthquake slip-in and submarine sliding. So I wanted to play the song, but somehow I couldn't manage. So I end my talk with one notion, which was like my take-home message here. When we talk about sliding, it may not be a big submarine landslide. It may just be peeling off the surface, and rather than slipping and sliding, it might be shaken and stirred. And I leave you with this message here, and maybe we get a chance to have a martini together and celebrate. Thank you very much for your attention.
Yeah, thank you very much, Mickey, for this very exciting talk about ocean discovery. And I'm sure many of the people in this room are very happy to see how you have been able to integrate these fantastic discoveries within the context of ocean drilling in the very big international community. We are out of time, but there is an honor ceremony tomorrow evening, beginning at 6 o'clock, where Mickey will actually receive that beautiful trophy. So we hope you will all join us there, or he's available after this session ends. Thank you very much for coming.